Hello Year 12, this is the introductory lesson to the energetics topic, AQA, A-level chemistry, going through some of the basics really that you have already met at GCSE. So not a huge amount that's new here, but it's going to be something that we will build on and develop as we go through future lessons. Now, as you go through, there's going to be a little pause sign that comes up, and that's where I want you to stop and do the activity before we go on and review it. So if you can use the slides that I've sent to you separately, you can put down the answers on there and then double check, make any corrections, but most importantly, I want you to think about any questions that you need to ask as a result of doing it. So let's start off with the first task. And on this, we are reminding ourselves what we mean by the terms exothermic and endothermic. So pause the video now and we'll look at the answers on the next part of the video. Okay, hopefully you've had a chance to do that and see what you could remember, or maybe you've even gone away and seen what you can find out from textbooks or online sources. But let's take a look at the actual answers. So for an exothermic reaction, heat energy is given off to the surroundings. Really straightforward definition, one that's going to be absolutely vital for you to remember. In terms of endothermic, heat energy is taken in from the surroundings. Now, as we go on through the course of this lesson, we're going to think a lot more about what that actually means and why it's so important that we remember it. Now I'm going to move on and look at energy profile diagrams. Again, you'll be familiar with these from GCSE, and I'm going to ask you to try to identify whether you believe that this represents an exothermic or endothermic reaction. So I would like you to pause the video and have a go. And what's really important here is that you are considering, first of all, what it is, but second of all, how you can explain that that's what it is, because that's the level of depth and clarity that you're going to need, certainly to get to the higher level marks as you go into exam papers and questions. Now, in the first instance, it's important to say that this represents an endothermic reaction. How do we know it represents an endothermic reaction? Well, energy has been taken in from the surroundings. That is obvious from this graph, but why is it obvious? Well, it's because the products have got more energy than the reactants had. So that must have come from somewhere. That's the energy that's been taken in from the surroundings. With all of that in mind, it should make identifying this one much easier, but I still want you to go through that process. I want you to decide, is this endo or exothermic? But more importantly on this one, it's about you explaining clearly why you believe that to be the case. Pause. And again, we start off with what's probably quite obvious because we know what the endothermic looks like. We can see, in this case, the products are lower. So we know that this one is going to be exothermic. Why is it exothermic? Well, from the definition, heat energy is released to the surroundings. So we're losing heat energy. And as we can see here, the products possess less energy than the reactants do. Going to move on now to look at some specific examples of exo and endothermic reactions that you are probably familiar with still from GCSE. Taking a look at the Whoosh bottle, and you can Google this, you can watch other videos on YouTube where you can actually see it in action, but it's essentially you are burning an alcohol in a big water container. Is it exo or endothermic? What is the evidence to support this based on what you can see and what you can measure? And I want you to have a go at drawing the energy profile diagram for it. So when you're ready, pause the video. And we'll start to go through those answers now that you've tried them for yourself. Now, question number one, very straightforward. This is an exothermic reaction. How do we know it's an exothermic reaction. What evidence is there? There's actually evidence just in the picture that we can see here, and that is that energy is being released to the surroundings. We can't see the heat energy being released here, but the flames do show that heat energy is being released, and indeed light energy is being released as well. So if the energy is being released to the surroundings, we know that it's an exothermic process. In terms of the energy profile diagram, we've got energy on the y-axis. I've added my line here for reactants and my line for product. My line for product is lower, and it's lower because that's representing the heat energy that's been lost to the surroundings that the reactants previously held. This is my energy change, but I'm going to show you it in a different way as well, and you may well have done this, but it's a slightly more complex energy profile diagram, one that you're much more likely to see. I've got my reactants and product lines there again, but I'm actually going to represent the fact that I need to put energy in. It doesn't just happen spontaneously. I needed to provide a spark. I needed a lit splint. I needed a match so that I could actually ignite those fumes of alcohol. And we call that the activation energy. Again, familiar to you from GCSE. So now we've looked at the Whoosh bottle, we're going to look at a different chemical reaction. We've got ammonium nitrate and barium hydroxide. Now this one you are again probably familiar with, but I'm going to tell you in this case it's an endothermic reaction. So you've got two questions here. What could we measure to support it, and what would we observe? And again, I want you to draw out the energy profile diagram. This time, irrespective of what you did on the last one, I want you to consider activation energy when you're drawing the energy profile diagram this time. So, pause. And now let's take a look at the answers. So if it's an endothermic reaction, we could measure the temperature. We could have a thermometer in there, and what we would see is that the temperature goes down. Taking a look at the energy profile diagram, and remember we're including activation energy here, I've got my product line higher than the reactant line. That's absolutely fundamental for a reaction profile diagram for an endothermic reaction. I've included my activation energy. Remember, that still goes up. This is me providing energy that gets me over that hurdle, that gets me to the point that my reacting, my colliding particles, my colliding reactants are actually reacting. And I've put in my activation energy there. It goes from the reactant line all the way up to the top of that peak. There's another line that you might be thinking of here, and we're going to move on to that in some of the next few tasks. Now we're going to move on to consider enthalpy. And we've got more learning objectives here, knowing what an enthalpy change is and describing what an enthalpy level diagram is. So we're going to build slightly on the energy profiles that we've done. And in the first instance, you are simply going to have to remember what the definition of enthalpy is, what the standard conditions are. I would like a symbol to represent an enthalpy change, and I would like to know whether exo or endothermic reactions have positive or negative values. So these are those 4 questions set out, and I want you to think about these. You're going to pause this in a second, write out your answers, and then check. So when you're ready, pause. And now you've had a go at each of those 4, we are going to look at each of them in turn. So the definition of enthalpy. Now, enthalpy is a very specific type of energy change that we're measuring. It is the heat energy change, but it's at a constant pressure. That's what makes it an enthalpy change, and that's the extra detail that you are going to have to remember. If we then think about the standard conditions for enthalpy, when we talk about standard enthalpy of formation and combustion later, it means it takes place under these conditions. Now, you may have needed to look these up. I'm hoping you did, and you're not just waiting to be given the answer now. The pressure is 100 kilopascals, and the temperature is 298 K. You will be expected to remember both of those numbers. If we then go on to talk about how we represent an enthalpy change, something that you will, again, probably be familiar with from GCSE, but we use delta H. So the triangle is a delta. It's a capital delta, not to be confused with the lowercase delta that we're very familiar with from our bonding knowledge, where delta positive and delta negative represent partial charges. But you'll talk about enthalpy changes as delta H. And finally, energy profile diagrams. You've already done a huge amount of this in previous examples, so I'm going to jump through. If I take my two options, the one on the left where I have got products with less energy, and on the right where the products have more energy. So from there, I know that the left is representing exothermic, the right is representing endothermic. I can now add my activation energies. I can show the hurdle that I need to overcome, the energy that I need to put in to initiate this reaction. But I'm now going to add another stage. And this is going to help us to understand whether delta H is negative or positive for an exothermic and an endothermic reaction. And if I take a look on here, you can see my delta H arrow on the exothermic is a downward arrow, and on the endothermic, it's an upward arrow. So if I think about moving down, that's a lower energy, that's a negative value. For an exothermic reaction, delta H is always negative. For an endothermic reaction, where you're going up in energy from reactants to products, your delta H is always positive. Moving on, we have got quite a lot of information here. I'm going to ask you to pause and read it. So pause. And now you've had a chance to read it and take that information in, I want you to answer the questions that are on this screen. So once again, have a read through, have a go, pause. And now that you've tried each of these, you can have a look at the answers as we progress through the video. So to begin with, drawing an energy profile for an exothermic reaction. I appreciate that this is quite repetitive. I know it's a task that you've already done, but we are building on and deepening that knowledge the more that you do it. And that repetition can be a really effective tool in getting this information embedded and ready for you to use in the future. Taking a look at it, we have got our energy on the y-axis. I've added my line for the energy of the reactants. This is an exothermic reaction, so my products are lower. I'm including my delta H. My delta H here is negative because it's a downward arrow. I include my hump that I need to get over, my hurdle, because I need to provide some energy, and I am showing that that is activation energy, EA, and it's going from the point of the reactant line up to the top of the peak. Now, in terms of the endothermic, I'm going to jump straight to the final answer here, but we will take a look at all of it. Fundamental differences are that delta H is positive on this one, that we are moving up from reactants to products. In terms of the next question, where we were asked for the fundamental difference between the two equations, I've put those equations back on screen again so we can see precisely what we're talking about. And if you look at them, there is only one difference between the two, and that's the state at which the water produced is formed. So the water is in a different state. In the top equation, we have liquid. In the bottom equation, we have gas. And then the final question, we've got two different enthalpy changes, and you had to identify which of the two would represent liquid water being formed and which one would represent gaseous water being formed. So I'm going to use energy profile diagrams to help to explain this again, and it might be worth adding some annotations and detail as I go through this, just to help you remember some of those key pieces of information. So I'm drawing my two energy profile diagrams out. I've not put the state symbols in for the left-hand side because they are identical. We've got H2 gaseous and half O2 gaseous. The state symbols are more important elsewhere in this diagram. In both of them, the H2O line, the product line, is lower because they are both exothermic. We know they're both exothermic because they both have negative values. I'm going to add my peak in. The activation energy for each of these is identical. We are still going to have to put the same amount of energy in. That has no impact on the final product that we make. But I'm now going to add the delta H's. And you'll notice from the scale of these that the delta H is bigger on the bottom one. So I have drawn and shown a notable difference there. And actually that helps us to see that the bottom one is representing H2O as a liquid and the top one is representing H2O as a gas. Key question here is why? Well, to get from H2O gas to H2O liquid, for it to cool, that means heat energy is being lost to the surroundings. So you would expect more heat to be lost to the surroundings when you're making H2O liquid compared to when you're making H2O gas. That takes you to the end of this particular lesson. It might be worth going back through this again. It's certainly worth making a note of any questions that are arising, anything that you're not sure about, and get in contact and do ask if there is something that you need to clarify. Thank you for listening, and I will see you next lesson.